The Majorana 1 quantum chip discovered strange irregularities in the most recent Pluto scans from the James Webb Telescope, leaving scientists perplexed. Strange signals coming from Pluto's frozen center have transformed what was supposed to be a normal examination into a cosmic enigma. Is this proof of highly developed alien technology? Or are rumors of a hidden ocean a natural phenomenon we have never seen before? Furthermore, this Pluto may be hiding information that would completely alter our understanding of life in the cosmos. An overview of Pluto's surprising marvels. Pluto was once thought to be a chilly, dormant planet. Astronomers initially thought it would be a frigid, lifeless dwarf planet. Pluto is surprisingly lively, however, as evidenced by the New Horizon expedition and photographs captured by powerful telescopes. Mountainous regions, level plains, and clues of something surprising beneath the surface astounded the researchers. Older theories about what might occur so far from the Sun were altered by these studies. Scientists discovered that Pluto's surface lacked the usual quantity of impact craters as they went over data and pictures. Meteor strikes have left scars on the surfaces of most of the outer solar system. Comets and asteroids should have left innumerable traces over billions of years. During its 2015 flyby of Pluto, New Horizons observed regions with few impact craters, expansive plains, towering mountains, and indications of active processes. Impacts from asteroids or comets should typically leave craters on a body in the solar system that has been motionless for eons. However, whole areas on Pluto seem smoother than anticipated, suggesting a surface renewal or repave mechanism. The presence of what appeared to be streaming ice was even more perplexing. Although a large portion of the ice is made up of frozen nitrogen or other volatile materials rather than water ice, in some places the ice behaves similarly to glacier on Earth. A hidden ocean beneath Pluto's icy shell could be a dramatic possibility as a result of these hints. Many planetary scientists, notably Alan Stern of the New Horizon team, began to think that there might be liquid water beneath the glaciers. The Tumor Regio, a sizable heart-shaped area, is a notable landmark. Sputnik Planitia, one of its lobes, is a massive nitrogen ice plain. Polygonal surface patterns imply thermal convection similar to that which occurs in a hot fluid. Even though the temperature differences are small, they seem to be sufficient to cause the ice to move slowly. In the meantime, mountains formed of solid water ice, which behaves like rock in Pluto's frigid climate, rise close to the margins of the planet's brilliant areas. The surrounding lowlands are elevated by several kilometers due to those mountains. Seeing such important topography on an entity that had previously been classified as inert was a huge shock. Scientists started to speculate that Pluto's internal geology is what powers it. Its ability to sustain a source of energy over billions of years may be due to a mix of residual heat from its genesis and ongoing radioactive decay in a rocky interior. Both vertical and horizontal movements would be caused by a partially molten or perhaps liquid zone beneath Pluto's crust. Old beliefs that anything outside of Neptune's orbit must be forever frozen solid are challenged by this hypothesis. Pluto instead becomes one of the increasing number of ice worlds that may have hidden oceans or heated interior layers, such as Europa, Enceladus, and Titan. Important questions were brought up by the idea that Pluto is geologically living. How is that much heat maintained in such a little world? Might it have begun hotter than anticipated, perhaps due to forceful impacts? If a warm layer is present below, is it made up of water combined with ammonia or another substance that prevents freezing at such low temperatures? Pluto's appearance gradually changed from that of a pitch-black, frozen rock to one with living activities. The prospect of the hidden ocean and the heart-shaped glacier. The luminous heart, a landmark that catches the eye in every picture, is one of Pluto's most alluring features. Sputnik Planitia, its left lobe, is thought to be a massive nitrogen ice plain. It is believed that slow-moving convection currents shuffle and refresh the ice because the surface is divided into polygons that resemble cells. The nitrogen ice's polygonal cells are tens of kilometers in diameter. There are few craters in that area, indicating a surface that is younger than the billions of years we might anticipate. It keeps getting smoothed out by something. Why is Sputnik Planitia such a focal point? Because this whirling glacier of nitrogen might be a secret ocean. This is the theory. If there is radioactive material in Pluto's core, it decays and generates heat. There may still be some heat trapped beneath an insulating layer of ice. Underneath the crust, there might be a reservoir of liquid or semi-liquid water. That layer could possibly be hundreds of kilograms thick if that is the case. Although nitrogen ice predominates at the surface, water-based layers may continue to exist at a liquid or slushy depth. Pluto's surprising orientation is one piece of evidence for this theory. Pluto seems to have rotated at some point, aligning its huge moon Charon with Sputnik Plania. Researchers believe that this reorientation was brought on by the additional mass concentrated in Sputnik Planitia and perhaps a subterranean ocean below, which minimized energy in their reciprocal gravitational dance. The term true polar wander refers to this shift, which suggests an interior layer that permits surface movement in relation to the core. The ocean idea is further supported by faults and fissures seen in other locations. The apparent long-distance nature of these cracks is consistent with the planet's crust gradually flexing and stretching. The crust might crack if a portion of Pluto's aqueous layer changed in thickness or converted to ice. You might anticipate different fracture patterns or fewer surface circulation indicators in a completely solid ball of ice. In contrast, Pluto appears to be geologically restless. Habitability debates are sparked by the prospect of a hidden ocean on Pluto. A subterranean ocean begs the issue of what might be beneath Pluto's surface, which is much too frigid for life as we know it. Energy sources independent of sunlight would be necessary for any life to exist there. Chemical gradients or hydrothermal vents might provide a way to support microorganisms. The existence of a steady liquid layer for billions of years is nonetheless revolutionary, even if life never developed. It increases the number of places where we could locate habitats that are based on water. Pluto's innards must be thoroughly studied in order to confirm the ocean. Measurements of gravitational fields, rotational wobbles, and surface fluctuations over time are commonly used in these kinds of investigations, but they call for a specialized orbiter circling Pluto, which does not currently exist. A future mission devoted to mapping Pluto's field and tracking its spin may determine whether an ocean indeed lies beneath its heart-shaped plains, but New Horizons only captured a fleeting image that offered only fragmentary hints, surface hints, and getting back on track. Pluto is unique in a lot of ways. In addition to being smaller than the moon of Earth, it and Charon have a unique orbital relationship that is so important that some refer to them as a binary system. They orbit a barycenter outside Pluto's surface, and Charon is around half as big as Pluto. The gravitational interaction between Pluto and Charon is influenced by this arrangement, which is unique in the solar system. Any significant mass concentration on Pluto could eventually be drawn toward Charon. Scientists observed Sputnik Planitia's direction, as if the dwarf planet had rolled around to lock in that feature just opposite Charon. They saw that it coincides quite precisely with Pluto's tidal axis. Pluto is no longer completely rigid as a result of its reorientation. It has the ability to move, suggesting an interior layer that separates the core from the crust. This kind of reorientation is a clear indication that there may be an ocean or a deformable layer beneath the surface. On the other hand, Pluto's surface is speckled with tall mountains composed primarily of water ice, which would act like rock at Earth-like temperatures. There are frozen peaks that rise 4 kilometers or more, a dwarf planet's unexpected appearance. There are smooth plains next to those mountains that indicate continuous resurfacing. Even the distinctions between different types of regions can be sharp or exhibit transitional characteristics that suggest dynamic processes that may be connected to temperature variations beneath the crust. Parts of Pluto's surface are covered with interesting patterns of ridges, troughs, and fractures. Extension faults imply that Pluto's surface may have enlarged, maybe as a result of subterranean water freezing or changing states. The crust may have fractured if Pluto's ocean had ever partially frozen and expanded into ice. Scientists attempt to figure together how long Pluto's interior has been partially liquid by analyzing the age and shape of these structures. The discussion has shifted to Pluto's interior makeup and temperature change over billions of years as a result of all these observations. Maybe Pluto was hot from the start. Some contend that a primordial ocean was formed when strong collisions during its development released enough energy to dissolve significant chunks of its interior. Over time, radioactive decay may have produced just enough heat to prevent complete freezing of that ocean. Pluto's ocean might be as old as the dwarf planet itself, if that scenario is true. Pluto may also have developed coal and warmed over time as a result of accumulated radioactive decay. In any case, New Horizons data clearly suggests that Pluto's geology is dynamic and still shapes its surfaces now. The possibility of life underneath the ice. Any hidden ocean raises an intriguing question for scientists. Would there be life there? Given Pluto's distance from the Sun, we must contend with its extremely cold surface and strong cosmic radiation. However, a deep ocean may remain more stable and protected if it is protected by a kilome of ice. Either residual heat from Pluto's formation or radioactive decay would maintain the ocean's temperature. If this is the case, microbes may exist, if they ever did, and survive by utilizing chemical energy from hydrothermal vents or other geochemical gradients. There may be life where water flows, according to experts like physicist Brian Cox. Our increasing understanding that life on Earth may thrive in harsh settings like deep-sea vents serves as the foundation for this theory. Simple life forms could emerge and survive on Pluto if the proper chemical composition is present in its innards. It's important to note, however, that there is currently no concrete proof of life on Pluto. Just a theoretical possibility exists. The concept of microbial life in such a remote location alone represents a paradigm change. We often anticipate life in a star's habitable zone, which is the region where temperatures permit liquid water to exist on a planet's surface. Scientists now suggest that even far beyond that classical threshold, internal heating can produce livable niches in the outer solar system. If verified, Pluto's ocean would be consistent with findings regarding other frozen worlds, like as Europa and Enceladus, which are also excellent prospects for secret life. It's interesting to note that an ice layer can act as a powerful radiation shield. Pluto may be surrounded by harsh cosmic rays, yet a lot of that radiation may be blocked by thick ice. An under-ice habitat might hold steady throughout geological time spans, providing a possible haven for any microbial community. Parallels can be observed in the polar regions of Earth, where lakes concealed beneath ice shelves are still liquid and home to microbes. Although Earth benefits from sunshine and a generally warmer climate, the shielding principle might still be applicable. However, it would be extremely difficult to prove that life existed on Pluto. We would most likely require a highly developed lander or orbiter, sophisticated instruments capable of detecting chemical residues, or perhaps the ability to dig through ice. Pluto is so far from Earth that even a one-way voyage takes years, making these missions challenging. A lengthy mission requiring specialized drilling technology may cost billions of dollars, making the cost equally intimidating. However, even the possibility of finding life on Pluto, no matter how simple, piques people's interest. The theory of hot start formation. How Pluto might have developed is one of the biggest changes in our knowledge of it. According to the conventional wisdom, Pluto gradually merged into a bigger mass after growing from tiny fragments of rock and ice in the Kuiper belt. Pluto would not have been able to retain much heat in such case, since it would have been extremely cold from the beginning. However, recent modeling points to an alternative route known as a hot start. In a hot start scenario, large impacts that generated enormous amounts of heat caused Pluto to form quickly. The initial core temperature of Pluto might have been high enough to melt a significant amount of water ice and form an early underground ocean if these collisions had formed the planet quickly. That ocean might have cooled and partially frozen over time, but not completely. Total freezing might be avoided if radioactive decay occurs in the rocky part of Pluto's interior. Pluto may still contain liquid water billions of years after it formed, according to this theory. Additionally, a heated start explains why Pluto's geological characteristics seem so vast. Its interior would have had more time to develop fault systems, glacier flows, and large-scale mountains if it had remained warmer. Cracks that have been seen may have originated when the ocean partially iced over, causing the surface to expand and fracture. Pluto's geology, which is dynamic, varied, and active, fits the description of an object that was never completely frozen to its core. Furthermore, new research on early solar system collisions suggested that the Kuiper belt was formerly teeming with massive planets that collided regularly. Such occurrences have the potential to produce local heat pulses strong enough to melt inner layers. Pluto might have acquired enough energy to sustain a partially molten interior for a very long time if it had experienced multiple significant impacts. Other ice worlds give us hints of potential similarities. But Pluto stands out for the volume of data, suggesting prolonged geological activity. The hot start model provides a reasonable explanation for aspects that previously seemed unimaginable on a small icy planet so far from the Sun, notwithstanding its lack of widespread acceptance. It also suggests that similar early heating may have occurred on other dwarf planets in the Kuiper belt, such as Make or Hera. If so, there may be more secret oceans in the outer solar system than previously thought. Thus, studying Pluto opens the door to comprehending not just one dwarf planet, but the whole community of frozen entities that orbit in the dark regions beyond Neptune. Expeditions and the difficulty of researching Pluto. It is no small task to send spacecraft to Pluto. It is typically 5.9 billion kilometers away from the Sun, though Pluto's eccentric orbit can cause that distance to increase. Launched on 2006, the New Horizons mission traveled approximately 9.5 years to reach Pluto in July 2015. New Horizons had a limited amount of time to collect high-resolution photos and other important data due to its quick flyby approach. Capturing Pluto's features required meticulous planning, and once the spaceship flew by, there was no turning back. Numerous discoveries were made possible by New Horizons. Glimpses of Pluto's smaller moons, details of its atmosphere, and the first close-up photos of the planet's surface. Because the mission just gave us a snapshot, it left us with many questions, but scientists were astounded to see the complexity that had previously been undetectable. Pluto was left behind with many uncharted aspects while the craft proceeded into the Kuiper belt in search of a backup destination. In a figurative sense, more than half of Pluto's surface is still in relative darkness because only approximately 40% of it can be seen in fine detail. There were calls for a special Pluto orbiter. A mission of this kind may circle Pluto for months or years, mapping its gravity, measuring surface changes repeatedly, and perhaps dropping penetrators or landers. A comprehensive investigation into whether an ocean actually lies beneath the crust and the evolution of Pluto's geology throughout time might be possible with that degree of dedication. Of course, money and technology are the problem. A durable power source would be necessary for an orbiter. Usually, a strong propulsion system and a radioisotope thermoelectric generator are required to enter orbit rather than simply pass by. Depending on propulsion and trajectory, the journey alone might take over 10 years. Once there, an orbiter needs to slow down sufficiently for Pluto's tiny gravity to grab hold of it. Complex gravity assistance have been carried out by missions farther into the solar system, but it is a difficult problem to travel so far out while still having enough fuel to enter orbit. A full-scale Pluto orbiter mission is probably going to cost more than $3 billion. NASA and other agencies prioritize a wide range of topics, including exoplanet research, Jupiter's icy moons, and Mars missions. Therefore, it's not an easy decision to spend that much money on Pluto. Nevertheless, a number of scientists contend that the benefits would be enormous. Verifying a subterranean ocean, closely investigating the composition of the surface and tracking Pluto's atmosphere throughout time would revolutionize our understanding of far-off worlds. Pluto, which was previously written off as an ice relic, may provide important clues about the early events of the solar system. Furthermore, each fresh piece of information from the dwarf planet can improve our models of how small, far-off things retain heat and change over time, which opens the door to more in-depth inquiries regarding possible species if we can verify that Pluto's ocean is real. Pluto in the context of the entire solar system. There are several other frozen worlds that scientists are interested in besides Pluto. Enceladus, which orbits Saturn, and Europa, one of Jupiter's satellites, have emerged as leading contenders for hidden oceans. Similar to Pluto, these moons exhibit geological features that belie their separation from the Sun. The surface of Europa is a fractured ice shell. Enceladus, which is thought to conceal a worldwide ocean that is heated by tidal forces from Jupiter's strong gravity, emits water vapor geysers via fissures at its south pole, signifying that there is water beneath the ice. These bodies serve as a reminder of the more general idea that, if they have internal heating, cold, remote locations can be geologically active. They may retain heat in different ways. For some, primordial heat and radioactive decay may sustain beneath liquid layers, whereas for others, tidal interactions with big planets are crucial. Pluto, on the other hand, revolves around the Sun without being pulled by a large planet. Its potential ocean, however, emphasizes how nature may find several ways to maintain water in a liquid state. In addition to Jupiter and Saturn, Uranus and Neptune are home to understudied systems. In the 1980s, Voyager 2 made a brief return visit to these planets, returning images of moons that might also contain intriguing geologies. The biggest moon of Neptune, Triton, features active geysers and appears to have been captured from the Kuiper belt based on its retrograde orbit. Another location that may or may not have had a subterranean ocean is Triton. There is a growing recognition that the outer solar system is full of possibilities, even as scientists prioritize expeditions to more accessible locations like Mars or Europa. Pluto is unique because it is located in the Kuiper belt, an area full of frozen objects. There could be thousands of dwarf planets in this system. Is it possible for additional worlds in the Kuiper belt to sustain geological vitality if Pluto can? Large members of this group, Eris, Make, and Ha, are known to have distinct characteristics. For example, Aries and Create have different surfaces with varying reflectivity, whereas Amira is elongated and spins quickly. Many things are yet unknown. Some or all of these objects would have had a similar story if Pluto formed rapidly and remained warm. The main point is that the outer boundary of the solar system appears to be far richer than previously thought. We used to think of it as a stagnant area with lumps of frozen, lifeless material. It is evident today that active geology is possible. In a way, new perspectives opened the door and made us realize how little we actually understand about diversity. In the upcoming decades, missions that explore the Kuiper belt may uncover additional ocean-bearing or geologically active worlds, pushing the limits of our understanding of the evolution of planets and dwarfs. Reevaluating the habitable zone and habitability. The distance that permits a planet's surface temperatures to maintain stable liquid water in the open air, such as on Earth, was the typical definition of the habitable zone around a star in the past. This idea clearly defined the range of worlds that were most likely to support life. But new information on Jovian moons, and more recently Pluto, has compelled a radical extension of that idea. Subterranean oceans encased in ice, heated by internal heat sources, and protected from cosmic dangers, seem to be potential hiding places for life. The possibility of an ocean on Pluto shows that conditions for habitability are not solely determined by direct sunlight. Water can stay liquid if the core contains enough radioactive materials, or if friction caused by tidally created forces and other energy sources are present. Scientists have conjectured that many exoplanets, particularly massive icy super-Earths or Neptune-like worlds, may contain vast sub-ice oceans as a result of this new viewpoint. Perhaps basic life, even orbiting stars far fainter than our own, finds refuge there. Analyzing Earth's harsh surroundings leads to similar discoveries. Without sunshine, life on Earth emerges in deep marine vents and thrives on chemical energy. Microbes are found in lakes hundreds of meters below solid ice in Antarctica. These analogies force us to recognize that stable circumstances and an energy source are more important to existence than pleasant surface temperatures and bright daylight. Even though Pluto is little and far away, it may teach us the same lesson. The flexibility of the conditions for life will be highlighted if a future orbiter proves the existence of a liquid ocean beneath Pluto's crust. In addition, it might force us to plan trips to other frozen planets to look for biomarkers, chemical indicators that could point to the presence of life. Some suggest, for instance, digging through Europa's ice or sampling Enceladus plumes as direct methods of looking for life. Although Pluto's plumes may be difficult to sample, its ocean would be just as fascinating if it were reachable. Therefore, when scientists talk about astrobiology, they now refer to mantle oceans or underground oceans, which include planets as far away as Pluto. The previously established limits of the habitable zone are upended by the simple idea that a location so tiny, cold, and dark may retain liquid water. This change affects our overall strategy for looking for extraterrestrial life, bringing attention to the possibility of life among frozen landscapes and uncharted oceans. We might only be beginning to explore the potential habitats that are dispersed throughout the universe, according to Pluto's geology, future prospects, and lessons learned from Mars rover's exploration. Our research of the solar system includes many other interesting missions that teach us about strange terrains and the nature of distant worlds, but Pluto steals the show with its hidden ocean potential. For instance, Mars rovers have shown how ecosystems can conceal histories connected to water. The discovery of ancient lakes, indications of flowing water, and minerals that form in moist conditions by rovers such as Sojourner, Spirit, Opportunity, Curiosity, and Perseverance has caused a significant change in our perception of Mars, from a desolate red desert to a planet that may have supported life billions of years ago. Even though Mars is far closer to us than Pluto, we can learn from the red planet about how to explore farther away. For example, every successive generation of rovers advances our capabilities in exploration, geology analysis, sample collection, and precision landing. Our efforts to push the limits of robotic science are demonstrated by Perseverance's proposal to store core samples for potential return to Earth. We can learn from these triumphs if we eventually try to send a sophisticated probe to Pluto. Although it is difficult, if technology continues to progress, it will be able to launch an advanced payload to the Kuiper belt, maintain communications, and perform in-depth investigation. Mars is not the conclusion of the planetary exploration tale. Comets, asteroids, dwarf planets, and icy moons all offer special circumstances that have the power to alter scientific perspectives. Even small bodies can surprise us, as demonstrated by missions like NASA's Dawn to Vesta and Ceres, Japan's Hayabusa asteroidal missions, and the Rosetta mission to Comet 67, Purium-Gerasimenko. Some contain organic molecules and minerals that are rich in water, while others may have hints of the early solar system. These revelations highlight how water and geological activity may be more prevalent than previously thought, which relates to Pluto's riddles. Lastly, the drive for human exploration provides further impetus. The goal of initiatives like NASA's Artemis program is to prepare the way for the possibility of human habitation on the Moon, and maybe Mars. Faster, more frequent journeys beyond the solar system are the goal of other private companies like SpaceX. That might eventually spread as far away as Pluto. Thanks for watching another episode. Please like and subscribe for similar content.